let's look at how we pick values of k. So the algorithms that we've discussed in this lecture, they all require us to pick a value for k before we can run that algorithm. So that leads to the natural question, how do we pick the appropriate value of k? So here's an example of a data set that is a plot of the two principal components from a problem in homework 8. So it was how states voted in elections. So if we look at this data, how many clusters should we have? Should it be 2, 3, 4, 5, 10, 50? What's the best choice? Now we can just make a subjective choice and see what we get, and then decide whether we like what results as clusters. So there's another approach we could use. If we're using k-means, then one approach is what's called the elbow method. So you plot multiple inertia values for different k values. So here, on the x-axis, we have 9 values of k from 1 to 9. And on the y-axis, we plot the inertia that we resulted from using that choice of k. And we can see that, and then we look at where we get diminishing returns. That's the elbow. Okay, so looking at this, when we go from k equals 1 to k equals 2, we see a significant reduction in inertia. Going from 2 to 3, there's a reduction in inertia, and it's pretty large. Going from 3 to 4, well, it's pretty small. And from 4 to 5, it's really small, and 5 to 6, and so on. So maybe we pick a value of 3 or 4. Because kind of beyond that, we're not going to see much reduction in inertia. So that's one approach. However, the challenge is that if you have really large multidimensional data, then oftentimes you won't see an elbow. So another approach is what's called silhouette scores. And it's a way of evaluating how well clustered a specific data point is. So the silhouette score, or silhouette width, of a data point is going to be high if it's near other points in its cluster. And it'll be low if it's far from the other points in its cluster. So the idea is that points in the center of the blue cluster, they have high score. Whereas that point that was the one we couldn't figure out whether should be yellow or blue, and k-means gave us one choice of yellow, and agglomerative gave us a choice of blue, that would have a low silhouette score. So for each data point x, its silhouette score s is going to be a function of 2 parameters. One is a. That's the average distance from that point to other points in the cluster. The second is b, and that's the average distance to points in the closest cluster outside of its cluster. And then the silhouette score is going to be b minus a, so the average distance from that point to points in the closest cluster minus the average distance to other points in its cluster, all over the maximum of those two different values. All right, so the max, we do that max to normalize so that we're over a range of -1 to 1. All right, so we can ask some questions. What's going to be the highest possible value for s, and how can that happen? Well, the highest possible value is going to be 1, because we've normalized things. And this will happen if every point in x's cluster is right on top of x. Right? So if you think about it, if that's true, if all the points are right together, then a is going to be 0. Right? Because the distance to other points in the cluster, they're all on top of each other. It's going to be 0. And so we'll end up with it being s being b minus 0, so that's just b, over the maximum of a and b. Well, that's 0 and b, so that's going to be b over b, which is 1. Now, what about the other direction? What's the minimum value that we could have? And can s be negative? Well, the answer is yes. The minimum value would be -1. And s can be negative when the average distance from a point to its cluster mates is larger than the distance to the closest cluster, right? And so if we look at that point with the low score, it's far from all of its cluster mates. It's kind of off by itself almost, right? And it's actually closer, we know, to the other points, the points in yellow. So that blue point, our low score point, it actually has a silhouette score of negative 0.13. All right, so we can compute all of these silhouette scores for each of the clusters, and then we can plot them. And that's what a silhouette plot looks like. So here, points with large silhouette widths, so closer to 1, they're deeply embedded in their cluster. They're near the center, they're near everybody else in the cluster, and they're far from other clusters. Points that have smaller silhouette scores are farther from that center and are closer to other clusters, right? And so here, the green that we tag as 1 represents our yellow points, and the larger silhouette plot here that's in kind of gray-black and is tagged with 0 represents our blue points. Okay, and we can see that at the very bottom, there's this silhouette score that's negative, right? What's that all about? That's the point we just talked about. That's our low score point that's kind of far from its cluster mates and near that yellow cluster instead. And so that's our negative 0.13 value. Now, we can take the average of our silhouette scores, and that's this dashed red line. Okay, so that average, that's something now we can use, because we can look at different values of k and see what the averages end up being. So here's different values of k. K equals 2 and k equals 3. And so you can see the two different colorings that result, sets of colorings. And for the two different silhouette plots, you can see that for k equals 3, the average silhouette score is lower. So maybe that's the one we should choose. We should choose k equals 3. Now, to be sure, we'd probably want to run this again with k equals 4 and so on. Okay, so that's another approach that we could use for picking k. Here's yet another approach that we could use to pick a value for k, and we're going to rely on real-world metrics to guide that choice of k. And this is an example from Andrew Ng at Stanford. So let's say you're producing shirts. All right, well, aside from style and other design questions, what sizes should you produce those shirts in? So you could think about two different alternative clusterings. So one is that we take and cluster the heights and width of customers with k equal 3. And we use that to design small sizes, medium size, and large size shirts. The other alternative would be we cluster the heights and widths of our customers with k equals 5. And we design 5 different shirt sizes. So extra small, small, medium, large, and extra large. So which should we do? Should we do k equals 3, small, medium, large, or k equals 5, and have lots of different choices for customers? Well, to pick k, because this is a real-world problem, we have to look at what are our projected costs and our projected sales for the two different values of k. Now, picking k small means I'm producing fewer sets of shirts, and I don't need as much different packaging. For k equals 5, I have to produce a lot more shirts, right? Because if I want to have, a certain inventory depth for a given size, I need to produce more in overall number of shirts to have k equals 5. So I'm going to spend a lot more money on packaging. Also, that packaging is going to be more expensive because I need more labeling and more marketing and signage for my stores and so on. But on the other hand, consumers like choice. And especially when it comes to clothes. Are they going to want to buy only 3 sizes, which means, what if I fall between small and medium, or medium and large? Or I'm really small, or I'm really large, then, the shirts aren't going to fit well, and I might buy a different brand, right? And so if we project our sales will be greater if we give customers more flexibility and a better chance of having a shirt that looks more tailored, then we might actually sell a lot more shirts. And that might offset the projected costs. And so really at the end of the day, we're going to make our projections and then we'll pick whichever one is going to maximize our profits. Okay, so in this lecture, we discussed a new machine learning goal, clustering. And we looked at 2 different solutions. We looked at k-means, and we looked at which tries to optimize the loss function called inertia. There's no known algorithm to do this optimally, and so we do approximations that may give us local minima for inertia, not global minima for inertia. The second solution that we looked at was an agglomerative approach, and our version of these 2 algorithms required us to pick a hyperparameter, k. We looked at 4 different ways to pick k. We could just do it intuitively by looking at the data, or we could use the elbow method, or we could use silhouette scores, or we could incorporate real-world information and metrics in making our decision for the value of k. Okay. Again, let's step back and look at the bigger picture. There are lots of different machine learning problems, and each one of these problems has many different solutions and techniques that people have developed. And each one of those techniques has many metrics for evaluating success or a loss function, or whether it's a good result or a bad result. And many of these solution techniques can be used for multiple different problem types. So for example, we can use linear models for both regression and classification. Now, this only scratches the surface, right? There are many very important ideas that are not covered in this class. We don't go through a lot of the algorithms behind these methods, but it gives you really a sense of the approaches that you can use. Now, one very important solution technique that we have not talked about and are not planning on talking about is neural networks or deep learning. If you want to know all about that, take another course in computer science or take one of the advanced data science courses to learn about that. We're going to give you, of course, some recommendations for specific courses to take if you want to learn more about the topics in this course. So, again, coming back to our taxonomy of machine learning, we have labeled data or unlabeled data. If we have labeled data, we can do supervised learning. We looked at regression and classification as 2 different approaches based on whether we needed something quantitative or categorical. We have unsupervised learning when we don't have labeled data, where we're just going to learn from the data that we're given. And we've looked at 2 different approaches there, dimensionality reduction, and today we looked at clustering. There's another approach we have not talked about at all called reinforcement learning, which is based on a reward function. And if you want to learn more about reinforcement learning, take a class like CS188.